Okay, so in this lab, we're just going to call it the rocket lab. Now, we may not get to the rocket part today, and the rocket part is kind of a minor part of the lab, so we might not even include it in the data. Here's the idea. The objective of this lab is to determine the mole ratio of hydrogen to oxygen in this reaction. Now, you could very easily balance this to get your hypothesis, right? So we're combining hydrogen with oxygen. This is basically the combustion of hydrogen. We're combining hydrogen with oxygen to get water. And we want to know, so the question for this lab is, what is the mole ratio between H2 and O2 in this experiment? Or in this reaction, I should say. Sorry. Now, here's how we're going to figure it out. We are going to use the assumption that the mole ratio equals the volume ratio. Now, you're going to see what that means in just a second, between the two gases. And then we're going to make a little device for collecting gases and for storing gases. What you do is you take one of these pipettes and you cut it off about 1/4 of an inch below the bulb. So you want to leave yourself at least 1/4 of an inch below the bulb, something like that. Okay? And the first step, which I'll show you in a minute, is we're going to calibrate this. So we're going to draw lines on this with equal increments of volume. So we're going to kind of make this thing like a little graduated cylinder. All right? And it's going to look like this then. You're going to have something like that, and there's going to be 7 equal increments. Oops, that's not 7. Now, one of the things, this lab handout actually says to make 6 equal increments, but we corrected that and made it 7, because what we want to do is we want to always leave this bottom part as a plug of water, because that plug of water will hold the gases in there. And what we do then is we actually fill this thing with different amounts of the two gases. So for example, if I made this one H2 gas, so if I filled the first 2 increments with H2 gas, and I filled the last 4 with O2 gas, then that would be a 2 to 4, or let's put oxygen first because I think that's what they do. That would be a 4 to 2 O2 to H2 ratio. And that's the volume ratio, but it's also the mole ratio. And a 4 to 2, of course, is a 2 to 1. Right? So that's how that works. So we can collect the gases in different ratios. All right. Now let me show you how that is done. What you do for collecting the gases is you're going to have a beaker, 250 milliliter beaker, and you put the bulb all the way under the water, and you just squeeze all the air out of it until it's totally filled with water. So now the bulb is totally filled with water. And then we have these two things. Now, one point of confusion is that on the handout, it says you're going to make your own gas generators. You're not. I'm going to have 4 stations set up with these white trays. This one is dissolving zinc and hydrochloric acid, making hydrogen gas. This one's making oxygen from hydrogen peroxide and manganese dioxide catalyst. So what I do is I put some hydrogen in here. Put this thing, well, all I did is I just slid this over the top of this little tube here. And then the gases bubble up. And they get trapped in this thing. Like so. Okay? And the water doesn't come out. The water's held in there. thing now contains a mixture of hydrogen and oxygen. Now, the basic method of our experiment is called continuous variation. And here's the basic concept behind it. Keeping total moles constant total moles, I mean H2 plus O2. Keeping that constant, in other words, it's a controlled variable. We vary the ratio. And observe the result. Now, what do I mean by varying the ratio? Well, if you look up here, I said we had a 4 to 2. I could just as easily have made a 1 to 5, or a 3 to 3, or a 5 to 1, or a 4 to, or a 2 to 4, or whatever. You follow me? Or a 0 to 6, or a 6 to 0. And your handout actually lays out the ratios for you on, I think, page 3 or something. There's a table. Now, so that's how we're going to do the different ratios. And we're going to do one, what I call dry run, when you're going to run through all the ratios just for fun, not really for fun, for practice, to get a handle on what's going on. And then 3 official trials. Replications, I should say. Replications of all, I think there's a total of 7 ratios. So in other words, you're going to do this 21 times in your official data collection, but 28 times total. Okay? If we have time. If we don't have time, then maybe we could use your dry run as one of the 3 trials or something like that, if we run out of time. All right, now, what do I mean by this? The result. What is it we are going to observe? Well, there's going to be a small explosion. So here's what you do. To get this, now hydrogen and oxygen don't react until they are ignited. So there's some activation energy required here. And to get this work. As long as I keep this upside down, the gases won't leave. When I turn it up, they could escape. So what I'm going to do is light a match, and if you don't know how to light a match, here's how you do it. There's a striking strip. Yep, be careful, there's a striking strip. You hold near the match head, you rub it vigorously, and you strike it vigorously on the strip. Now it's lit. Now watch what I do. I'm going to hold this upwards. And as I bring it up to the match, I'm going to squeeze it gently. The gases will come out, and it will ignite. And you heard the pop. Now, this one didn't work that well. Hopefully, you have a little, like when I just did it this time, I've got a little plug of water there. When you turn it up, you hopefully will have a plug of water that will keep the gas from escaping until you give it a gentle squeeze. Right? Now, this configuration of my hands right here is a controlled variable. It's a variable I want to control. So keep that in mind when you're igniting this. This process, when you bring this up and gently squeeze it, is part of the variable in this, part of what's varying in this experiment. How hard did I squeeze them? How fast? How close is the flame? Yes? Okay, yep. So the next thing is, how do we make that data? This is where this gets kind of subjective. We are going to record a rating for how loud the pop is. And you can do 1 to 5 or 1 to 10. Your packet is set up for a 1 to 10, I think, rating scale. This is why I say do a dry run, because you can get to hear the full range of loudness. and then start to get a feeling for your rating scale. So, you're going to give it a rating, 1 to 10 or 1 to 5. 5 being the loudest or 10 being the loudest. So maybe that was a 2. But again, I don't know if that's a 2. I know it's a 2 because I've heard how loud they get. So that's why we need to go through all of them first. So go through them all once, then you develop your scale. Now, we're going to use blind trials on this. You guys, many of you already probably know what the mole ratio should be in that reaction. All right? That's going to cause you to be biased toward that ratio when you're listening to it. So here's what we do. The person who fills this bulb is not the person who gives the rating. So the person who fills the bulb knows the ratio. The person giving the rating does not know the ratio. You follow me? So it's called a blind trial. So that eliminates the bias idea, where you might expect a certain ratio to be highest, so you tend to hear it as higher, which is a very real possibility. Okay? So we're going to use blind trials. If you want, you can switch off on the blind trials. So like you could go all the way through all 7 ratios with one person doing the rating, and then go through the 7 again with another person doing the rating. It would increase the uncertainty, but then again, it might eliminate some problems too, depending on how the person's rating. Some people tend to hear all the sounds like the same loudness. If you're one of those people, then you probably shouldn't do the rating. In other words, if you start listening and you're like, I don't hear any difference at all, then let your partner do the rating. Okay? Because otherwise you're going to get like a level graph, and it should not be a level graph. Okay? So blind trials, you can switch off if you want. Keep an eye out for what you're listening to. So our end goal here, folks, is real quickly, you're going to have a graph, and it's going to have the ratio down here between hydrogen and oxygen, probably in decimal form, because then you can make this a scatter plot. So in other words, if it's a 1 to 1, that's 1, right? If it's a 2 to 1, that's 2. If it's a 1 to 2, that's 0.5, and so on. 0.25, whatever. And then over here, you're going to have the rating. And then you're going to see what this graph does. And the idea is that the maximum pop comes from the best ratio, the optimum ratio. And why that is has to do with limiting reactants, which we're going to be getting into with this homework and then next week. The maximum pop comes from the optimum ratio. All right, and then last thing before we get started, the calibration process. This is the process whereby you are going to put lines on the bulb. Here's what you do. Real simple. Well, it's kind of simple. Squeeze all the air out of it so it's full of water. Find the total volume. Divide it into 7 equal increments. So it turns out that most of these are about 4.9 mils. Okay? If they're 4.9 mils, then that divides evenly into 0.7 mils, 7.7 mil increments. So here's what I'm going to do. Every 0.7 mils, I want to make a line, starting at the rounded end. So what I'll do is I'm going to squirt out 4.2. Okay. Because this one was a little bit more than 4.9, what I'm going to do is start at the other end. I'll show you what I mean by that. Squirting out 4.2. Now the airspace in here is 4.2 milliliters, right? So what I'm going to do is, wait a second, how does it work? That looks like too much. extra to be the last part that's going to be always water. I want the top 6 to all be 0.7 minutes. So the reason I'm not squirting out 0.7 is because there's no lines below the 1 mil mark on this graduated cylinder, so I can't. I have to go backwards. So see, that should be. I guess that's how it's going to be. So this is going to be. Maybe I should. So I'm going to make a line there. And then I mark the water level. Now I do it again. This time I'm going to blow out 3.5. Follow me? 3.5. So I'm going in increments of 0.7 here. Now this is an important step because this gives you your lines. If your lines are off, then your data is going to be off. Right? So I'm going to do like this. And keep going. So one big source of error on here is your initial lines. The other big source of error is when you're filling these up with hydrogen gas, make sure you go to the line. And it's kind of tricky because sometimes these are going kind of fast and you have to, the bubbles are going to go up in here and you got to try to stop them at the right place. 3.5, now I'm going to pour out 2.8, right? Okay, that's 2.8. And something's going on. I'll let you guys mess with it. So, that's a tricky part. If you really mess it up, you can grab another bowl. The markers are here. You may want to put a piece of tape over your lines when you're done so they don't rub off. Keep putting on the water and everything. All right. You need to wear goggles. The